Which I was very close to thinking it's fine.
If you make it big enough, you could show somebody and thinking it was one of those eggs that.
Yeah, I can show you. I'm showering in a while.
What's the name of that?
Dimitri, do you want some chocolate?
Oh, I appreciate it very much.
And if you want chocolate, it's like.
Eddie.
You want chocolate? And so
Thank you.
Does anyone have the list of subjects from last time? To the extent that we free you to sacrifice it for making it a sign-up list. Okay. And since you are sacrificing it, you can start. Oh, Amelia is quicker. You may please express your wishes, and I may slightly update what you will be signing up. Like the stuff that you did last time, like originally in the list from here up to there. It looks like someone may think that it is one subject. It's too much for one person. You need to chop somewhere in between. And I don't know what is the choice of Steven. You may, if you are online, send an email with your choice. The applications are very easy, and they are last thing to choose. So let's first populate stuff before and have it as a backup. Because it's super easy, and everyone will get it without help. It's like, I know what I'm telling you, it looks like more advertising to take it quicker.
So we're signing up for like sections?
What you can do is to write like, for example, I want this and this and this, like, and I believe that 3 will be enough for me.
Should we do about 3?
Well, we need to populate everything.
Okay.
So not a single person has to do all of the numerical modeling on it.
No.
Okay.
No. So, but if there will be some undersigned sections, then I will select myself to do them.
So if I selected just movies, I should select more than that.
Yes. Yes. There are some.
Steven's connected.
Huh?
Steven is connected.
Yeah. Hello. If someone would be willing to split the numeric modeling of quantum dynamics, I would be willing to do that with them.
You want the first half or the second half?
I would prefer the second half.
He wants the middle.
So you want this communication of operators and conversion of operators?
No, the lower.
No.
He wants
Oh.
the discrete
The-
optimization size.
Wow. Oh, okay. So you want the second half?
Yes.
Okay.
I'll get you down for it.
Thank you.
Thank you, Steven.
Please do not get theory. That was the last. It's hard in that thing. I don't want this.
Hard theory.
John's already got it.
Oh, thank goodness. Yeah.
You're doing it for those.
I just want to see if I have control to focus camera either on podium or on the class.
They really think they're gonna have to spend for this like $2 for this because
I care only about what is being broadcasted and recorded. What is shown, it doesn't matter.
Okay.
Okay, so who we are and what are we doing? So we are preparing to present methods of this quantum dynamics modeling in not the coming week, but next week on Monday, right? And it looks like everyone approves this date. If it is inevitable to present, then Monday, November 1st.
I'm sorry?
Huh? Monday, November 4th.
Yeah, we have an exam with it, but
Huh? But you can prepare earlier, right?
yeah.
There was an opinion to do it on Saturday. And if you do it in the middle of the week, probably there will be less time to prepare, and you will forget your previous preparation.
It's gonna be real weird.
Yeah. Okay. Are you selecting something in the alternating order?
I didn't do anything. It was just a few that were missed. So.
Okay.
I think I'm gonna do it.
Yeah.
I'll probably extend the borders. Like if there is a missing subject between two speakers, I will assign it either to quiz before or after. But if someone selected like 7 subjects, it's safe. I probably will withdraw. So for good. Thank you much. Thank you much. Appreciate it. Okay. Makes sense. So our goal is to predict outcomes of measurements for characterization of materials. Since electrons in molecules are quantum particles, we learn the quantum laws of nature, and then apply it to a sequence of objects. At the same time, we get, although you already are proficient experts in laws of quantum laws of nature, we are getting more and more practical tricks, computational tricks, or math tricks to solve this problem. And we have completed 3 space, 3 box, and now we are starting something that oscillates. Today there is no time, but one day during this chapter we will discuss what are possible examples, what can oscillate, in addition to 2 atoms in a hydrogen molecule, collective electron motion, cosmonic particle, stuff like that. And maybe there will be a little quiz where it will be not challenging, but there will be at least 6 options what can oscillate in chemistry. Just giving heads up. So a little outside of the major subject, the stuff that we are presenting, I think those are whiteboard captures from last year. So we do need momentum, which is derivative of a position in 1 dimension of gradient in 2 dimensions. Derivative is infinite difference is subtraction, and in the lab we apply definition of differential operator of derivative to discrete space. Then in the finite differences, the matrix for derivative should look like zeros on the main diagonal, 1 on the upper subdiagonal, -1 on the lower subdiagonal, and relevant constants outside of that. It is subject that Morgan is doing. And then this stuff is plugged into common plan and into the evolution theory of where this is being. The initial condition includes multiplication of Gaussian shape times plane wave to have things moving forward like buttons. Because we want to have connection to intuitive understanding of classical world or whatever particle and world. Why it is needed? Because momentum is motion and motion is temperature. If you will use this package to describe chemical reactions, you can increase temperature by assigning quantum momentum. shown conversion operators between momentum and position. Remember, and we will start actual lecture soon. I remember when we were doing homework number whatever 2 or 3, when we were practicing transition from Gaussian wave packet to expansion coefficients in basis of plane waves. So it was our preliminary step to get the concept of uncertainty. So that in coordinate space, we started with Gaussian wave function, and then when we found expansion coefficients, they were looking like Gaussian function as well. Okay. And in space of expansion coefficients against the plane waves, index of each expansion coefficient is value of momentum. So therefore, it can be interpreted as momentum space instead of coordinate space. Make sense? So it's space of expansion coefficients or momentum space because momentum is index for each expansion coefficient. And if in the momentum space we do want to express operator of momentum, it will be not a derivative anymore. It will be just diagonal with values of momentum. Negative, negative, 0, positive. Same as in the coordinate space. Operator of position is just x, independent variable, not derivative. There is a symmetry. If we go into momentum space, then momentum becomes, operator becomes just p. And if we need position, then we need to do derivative or something. But in momentum space, momentum operator is just matrix which is diagonal. Another piece of information. I plan to cover it in the labs, but it's better to give a little heads up. But now it is like a private lecture for John. When we translate wave function from position space to momentum space, we do Fourier transform. We multiply it by exponential and integrate. If you go from position to momentum, we integrate over x. If you go from momentum to position, we integrate over p, or whatever with that. So to translate wave function, we apply Fourier transform once. Because the function is a vector. Any operator is analogous to a matrix with two indices. How many times we need to apply Fourier transform if you want to convert an operator from momentum to position space, or from position space to momentum space? Yes. So if we express momentum operator in terms of in the momentum space, and we apply Fourier transform twice, so here is P prime, dP prime, then we will get momentum operator in X space. You already know that for momentum operator, I'm going to go one step, is matrix with 0, +1, -1. But it is an approximation. If you do it through Fourier transform, the definition of momentum operator will have some corrections. So the second subdiagonal, upper subdiagonal and lower subdiagonal will be not 0 but smaller number, like 1/2 or maybe 1/4. And then it will decrease, becoming smaller. So it's additional corrections. And if one compares this everything computed based on this dumb definition and more advanced, then the results will be substantially more precise. So, where did we stop last time? And I'm skipping a review. We were talking about Fourier transform, examples, and we used the connection between rigidity of a spring, or whatever curvature of the potential energy surface, mass of a particle that is oscillating, and frequency of oscillation. And when we plug in this frequency into potential energy, you get the potential energy will equal mass, frequency squared over 2, deviation squared. So this is our potential energy. Kinetic energy is standard for the time. And here is time into potential energy equation. Kinetic, unknown function. Potential, unknown function. Unknown energy, unknown function. So in a narrow sense, our goal is to solve this equation, no matter what it represents. In a broader sense, we need to provide theoretical fundamentals to describe phenomena, oscillatory phenomena in oscillating molecules as a primary target, but there are several examples which oscillate and exhibit quantum features. Who can solve this equation? Like, I know we can solve, we can open Wikipedia or text on differential equations, but do you have an immediate idea of what to do with it? Like, if this would be a constant, then we would just plug in exponential as we would guess and find coefficients. But it is not constant. It's proportional to second power. Even if it would be first power, I would do it right away. The second power creates substantial, it looks like a short, concise equation, but it takes substantial effort. So the standard, there are two groups of books. If you want to abandon lectures, study everything with yourself and books, and then come give me an example. I know it better than I. It's normal, it's possible, but you'll find there are two types of books. One type will just declare answer. Another type will apply recursive method and find solution in form of series, because the answer for this Schrödinger equation has more than one answer. Answers to this Schrödinger equation with this potential will have answers that are not expressed as sines, cosines, exponentials, or polynomials. It will be something more complicated for which we do not have name. And it is a frequent situation in differential equations. If differential equation generates something crazy, but regular and studiable, learnable, then one goes, oh, okay, it's a solution in special functions. And whoever first declares it names the function according to his acronym. So the solution of this equation will be Hermitian polynomials times exponential, and standard mathematical way is to represent this unknown function as Gaussian exponential times unknown series. So like r square, r third with coefficients. And this is the second part of the equation. You can do it. You have sufficient background, but it will be painful, and if you do not skip steps, it will be like 3 lectures. I want to offer a shortcut, which may take like 2 instead of 3, or maybe 1 instead of 3. And the shortcut that I'm going to offer will be like 2 birds with 1 stone. On one hand, we will solve for the solution. On the other hand, we will get 1 more method that will be very general and applicable not only to oscillations, so it will be a new concept. So, what are we expecting to get after practicing all this stuff? So, this is expected outcome of today's meeting. If I will be quick and finish everything in the remaining 24 minutes, this will be the last slide. So the solution, the lowest energy solution for potential that looks like parabola from this later will look like Gaussian function. Exponential minus elongation squared, and then there are some constants. And I may have committed some errors in this constants, so do not believe me right now. I hope to correct it at the end of the video. So the analysis and positive knowledge that there is a similarity between particle in the infinite box and harmonic oscillator. If we forget about implementations in real life and just think mathematically. In both cases, lowest energy state looks like a camel with one hump. So the wave function doesn't intersect zero. Second, it will not be shown today, but maybe on Monday, that the energy of the lowest state is larger than zero. So there is a 0-point energy. In the box with walls, the height of this energy was the higher the smaller the box. Here, parabola formula is defined from minus infinity to plus, but it has different curvature. So the larger the curvature, the bigger is ground state, 0-point energy. It's inverse of the fact that here will be also the steeper the parabola, the smaller the width. The shallower the parabola, the wider the width. This width determines uncertainty of position. So if it is very rigid oscillations, the position, interatomic positions will be very certain. If it is, so like it is hydrogen, H2-, they will be exhibiting quantum properties, but distance hydrogen to hydrogen is rather certain. If it will be something heavier like iodine, because of high mass, it will be much shallower parabola, and the uncertainty of position will be much bigger. So they will be, no one knows how far close to each other. Okay. So we have about 20 minutes for the actual lecture. Suppose we have house, or we don't have house. We have just a stair. We have a soil level and stairs, and we have this stickman walking on the stairs. Stickman can go up and go down. The journey of stickman will be converted into mathematical tools. Let's assume that we already know solutions for the Schrödinger equation, so that we know wave functions and we know energies. And then let's design a stickman that will walk between the states, so that the stickman can go only one ladder up or one ladder down. So if this creature goes one step up, energy increases, one step down, energy decreases. And we will find how this oscillatory stuff will look for each state. So nothing criminal in this idea, right? Not super exciting, just okay. But I'm going to offer a little logical confuse. So if you are in the middle of the stair, you can go, and the stair is infinite. You can go as far as we can go up. If you're going downwards, Can we go infinitely down if we are staying on a solid ground? So the operation of going lower than the lowest state is not allowed. It's just committing suicide, trying to hit the ground, or I don't know. It's not permitted. It doesn't exist in this nature. Okay? You agree with this logic? Then you are basically done with this chapter. The rest will be just limitations. So you cannot go lower than the ground. If you try to mathematically practice jump lower than the ground, result of this operation will be zero, nothing. Not a vector, not a matrix, not a function, just nothing, zero. I was very angry on my instructor when it was taught to me. So they're like, no. So if we do have a function, and we have this stickman, like weather operator walking up and down, what does it mean different weathers? If you have a function for level number n, and we apply this operator coming up, it will become n plus 1. If you apply jumping down, it will become n minus 1. But if n is already equal 1 or like 0, we cannot go to minus 1. So operation of going down, let's call it a, going up a plus, going down a without. So going down from lowest level will be 0. So this trick, if carefully processed with math, will save like 20 pages of derivations. And if you generate solution for Schrödinger equation for those three. There is another thing that I will try to speed up because it's not super complicated, but it is boring. I'll just communicate your idea and quickly go through slides. Fortunately or unfortunately, it is not a comedy club, it is a science class. Right? So the stickman goal is not only to entertain all of us. It's a mathematical concept to get the answer to describe this stuff that oscillates. And through our previous experience with quantum theory, physical chemistry, we already, maybe you are not, but I'm already, we are becoming like robots. I see quantum problem, I first write down Hamiltonian, and then I try to find solutions to Schrödinger equation. What is the connection of this stickman jumping on the ladder up and down and Hamiltonian? If this going up and down ladder is an operator, is there a chance to formulate Hamiltonian in terms of this browsing, bless you, up and down through the ladder? It sounds a little crazy. I hear it for the first time. So, on one hand, our Hamiltonian is elongation from equilibrium squared and from matrix squared. Okay. Here is the hypothesis that I do not have excuse. It's just a hypothetical statement that is not proved yet. But what if our operators of going up and down through the ladder can be expressed as linear combination of position and formula? Like, I put here P1, P2 because it is plus, and M1, M2 because it is like minus going down. So is there a way, and there is one more properties of this stickman. So we already observed, and you are not objecting, which I interpret as agreement, that statement can go lower than ground. But what if this crazy creature decides to go one step up and one step down immediately? How do you interpret it? Nothing is changing. So like wave function changes from where it was to one more and then returns back. So it's identity operation. And probably it can be connected with, we are staying on the same level where we were. So through this operation, hypothetically, we can extract number of stage where we are. And maybe, again, it's all hypothetical, but I will bring bones to this, bring me to these bones. Hypothetically, this operation of going up and down immediately can bring us energy and bring us Hamiltonian. So hypothetically, if you go this way, down and up immediately or up and down immediately, it will bring the Hamiltonian. And by now, you do not need to believe it. It's only a hypothesis that may or may not hold. But in order to check this hypothesis, I may want to construct product of these two linear combinations and find coefficients in such way that as a result we will get two Hamiltonians. It's not forbidden because we will not get power higher than r squared and p squared, and a constant can pop up because of r and p do not combine. We generate some penalty for sorting the effort.
I'm sorry, is R equivalent to X?
R is like x, yes. Why I do not use x? Because x, well, we can use any variable. It's not a problem. But x means that you have one-dimensional problem, and it in a specific axis of Cartesian space. But if we use letter r, it implies that it is distance, which can, like, hydrogen molecule can rotate in space, and this direction from one atom to another doesn't need to be aligned along the x-axis. So r seems better here, but I do not insist. For your request, I can pick to replace each r to
Oh, no,
x.
I was just making sure.
Okay. Okay. So I will try to be as quick as possible through this operation because I hate it so much. But I think you got the concept. Like, if we find these coefficients, and if this hypothesis is correct, then our Hamiltonian will be a little simpler. Okay? So we just need to find which coefficients to learn. How do I do it? And, property number 3. One, you cannot go lower than ground. Second, if you go up and down, you stay where you are. And second, we want these operators to be Hermitian conjugate, so that by applying Hermitian conjugation, like complex conjugation and swapping from we will change the direction of action of this operator. If we apply Hermitian conjugation to ladder up, it will become ladder down, and opposite. If you apply conjugation to ladder down, it becomes ladder up. Okay? One conjugation will become make it plus. Two conjugations will become the down. Coefficients, making this two stuff equal. And carefully solving for the stuff by finding the properties. if I open the brackets, then product of P1 and 1 should be factor in front of kinetic energy, P2 and 2 should be factor in front of potential energy, and the cross terms should connect to commutation product. And also the P1 and 1 and P2 and 2, because of conjugation, they will become equal by absolute value and opposite by sign. One of them will be imaginary. So it's 1, 2. Solved as square root of the factor in front of kinetic energy. So, and it should be the same uppercase over bottom. Planck constant, square root of mass in the denominator, and imaginary unit because it was 1. For P2, it will be square root of the factor in front of potential energy. So omega, it was square, now it is linear, and then square root of mass over origin. So if we, it's just a repetition of this details. Processing. Then we are plugging in these coefficients P1, 2, and 1, and 2 into linear combination of position and momentum operators. And by now, you do not need to believe it. It's all hypothetical. It's a demonstration rather than rigorous proof. But later on, you will see that it is true. So by plugging in the coefficients, we see that this lowering and raising operators are expressed in a certain way as linear combination of position and momentum. And the logic of these coefficients is because by our free will of free humans, we want to cast Hamiltonian in terms of this up and down operators. So in some sense, it is made up construction to make our life easier. And you may think that everything we do here is suffering. But I'm showing the path of least suffering. If you would otherwise, it would take much more. Or if you want, you will not do it all, we will miss important components of skills and education for those who want to do academia or want to teach this stuff for others. Very good subject for this. Okay. Now, I think we are 5 minutes, and I will be able to get to the finance. So suppose that you either believe me or you pretend that you do, or you postpone proofs of all the statements for the future. If everything we discussed is correct, and one cannot go deeper than ground, then applying this so-called annihilation operator or weather down operator, which is position and momentum in these certain conditions, to the unknown ground state, will generate 0. So typically, by applying, I'm trying to deliver it as an instructor that when I was sitting in the class for this subject, I was like physically angry to the teacher. I thought it is a wrong idea. It's like against any logic. Because everything was taught before. If one applies operator, the function, one should get another function. Right? Here we are breaking the trend. It's like going against rules or against the patterns. But the logic is that you cannot go deeper than ground. It's forbidden. Therefore, there is a unique thing. And this unique thing, acting by operator for a function we get 0, you will see it in like 2-3 minutes. Makes one. So, agreed. Now let's just process it mathematically. So momentum rate replaced by negative I on constant derivative. And one can identify that first term is, if we forget about constants, we can put them back later. So it's independent variable times unknown function plus derivative over independent variable times unknown function. Can you solve this equation? Right? So it's a little easier than having independent functions squared and the third. So how do we solve it? I do not know that you have an idea, so we bring one part on left and right, and then we divide both, multiply both left and right by increment of position, and divide both parts on the independent function. Then everything on the left will be only position, everything on the right will be independent function, right? And then you can apply just line simple integration to left and right. So on the left you integrate RDR, on the right you integrate derivative of function over the function. What will be the integral? This will be R squared. I know what you do. They need help with this. Huh? Yes. Okay. Everyone agrees. Just the same thing. That way is called for efficiency. So, for square and making them equal to each other. Log is equal R square over 2, right? You agree with that? And if you take exponential of log, it will be just argument. And if you take exponential of R squared, it will be R squared. So around, if we follow this logic about stick man going below the ground, trying to go below the ground, then out of this logical step, P ground state of harmonious oscillator should be e to the power minus R squared over 2, which is known to be a Gaussian function. With inverse of this stuff in the width of this Gaussian distribution. Right? But I think I corrected at the beginning. I was trying to wrongly put here, and there are two, but they're not here. It's first power of frequency. Good. Looks like Gaussian center of equilibrium, similar to ground state in a box. Yes. And we do have a normalization constant that we didn't define yet, but I think we can put for doing it next time. With your permission, I would like to announce the meeting accomplished and wishing you a nice weekend.